It's my pleasure to introduce Jie Li, who is a postdoctoral associate in chemistry in my laboratory. And Jie comes to us originally getting a bachelor's degree at Nankai University in Tianjin, China. And then she I think it's the second largest city in China. It's a very big place. And yes, I've been there, and it's a very good university. And then she came to the United States to get her PhD in chemistry at Brandeis University. And there she worked with Bing Zhu, who Bing was one of my very first graduate students. And so I am actually Gia's academic grandpa, but she doesn't call me grandpa. She's very polite. And she did very biotechnology type things and a kind of interesting blend of chemistry and biotech at Brandeis. And so in my group, we were really interested in getting into much more biological applications of colloids. And that's a new area for us. And so Jie has been really the kind of point person in pushing all of these things forward. I think you'll see that she's really been quite masterful at how you take droplet technologies or complex colloid technologies and really transform them into biotechnology for biosensing. And so with that, Jie, you have the floor.
Okay. Thank you, Tim, for the kind introduction.
Just one thing, Cerise, I forgot a couple things. One, make sure all your microphones are muted. And at the very end, we'll just raise your hand and we'll take questions. Okay.
Okay, thank you again. Hi, everybody. My name is Jie Li. I'm a postdoc from Professor Tim Swagger's group. And it's a great pleasure to give a talk in the Nano Exploration series. And today I'm going to talk about fluorescent Janus droplets and its application in biosensing of Listeria Monocytogenes. And before we talk about our fancy project, I want to just give some brief introduction about dynamic complex liquid colloids. So dynamic liquid colloids are composed of equal amount of hydrocarbon and the fluorocarbon two phases by dispersing the two phases in the continuous water solution. The dynamic liquid colloids are, as we said, dynamic, and we can change its morphology by changing the concentrations of the surfactants in the continuous water phase. Here I'm showing two very frequently used surfactants in our group. One is twin 20, which is a hydrocarbon surfactant, and the other one is zonal, and it is a fluorocarbon surfactant. We could see the change of the morphology of liquid colloids with the different ratios of those two surfactants. And we can see this scheme from the very left. With a higher concentration of hydrocarbon surfactant existed in the water continuous phase, the morphology of the liquid colloids will be the double emulsion with the fluorocarbon encapsulated by the hydrocarbon. And when we keep adding the fluorocarbon surfactant into the continuous phase, and the morphology just get to a different type, we call it Janus. A Janus droplet is composed by you can see that both of those two phases occupies one hemisphere and just form this morphology. And we further increase the concentration of the fluorocarbon surfactant. Now the morphology keep changing and getting to an inverted double emulsion morphology. With this morphology, we could see that the hydrocarbon is encapsulated by the fluorocarbon. And now we know what are the dynamic complex liquid colloids, and I'm going to talk a little about the applications of the complex liquid colloids. Lauren, who was our previous colleague, and she demonstrated that the dynamic liquid colloids could be used as micro lenses. And because the morphology, with different morphologies, the dynamic liquid colloids will have different optical refractory properties. And we could see from this figure A here, when the light is trying to pass through a layer of the droplets with different morphology of the liquid colloids, the light will show a different propagation direction. And when the light is trying to pass through the double emulsion or the inverted double emulsion, we could see that the layer of droplets just altered the direction of the propagation of light. Only when the light is trying to pass through the Janus droplets, the direction of the propagation doesn't change. And this optical property will be observed by our naked eyes. And Lauren just did this very simple experiment, and she put a layer of the droplets with different morphology in a petri dish and put the petri dish on a piece of paper with a smiling face. We could see that the double emulsion or the inverted double emulsion solution is opaque, and we could hardly observe the smiling face through the emulsion layer. And because the light propagation direction will not be changed by the Janus droplets, the solution of Janus droplets actually is transmissive, so we could easily observe the smiling face through the layer of Janus droplets. And also, Lauren just made use of this property to do the measurement of enzyme activity. Figure C demonstrates how she did the experiment. She just put a cyclodextrin and Triton 100 complex, which are ineffective hydrocarbon surfactant into the continuous phase. So because at the beginning, the hydrocarbon surfactant is ineffective, so the initial morphology will be hydrocarbon in fluorocarbon double emulsion. With the addition of alpha amylates, the effective surfactant Triton 100 is released gradually. So the final, the morphology of the double emulsion will kind of like slowly, gradually changed into the inverted double emulsion with the hydrocarbon covering the fluorocarbon. And this process could be tracked by measuring the transmission intensity, and also by measuring and recording the transmission intensity, she was able to quantify and measure the activity of the enzyme amylase. And another class of application of our dynamic liquid colloids is that we can do bacterial sensing using those droplets. And here are two strategies. One is agglutination assay designed by Qifan, one of our previous group member. And the Qifan designed a mannose surfactant that could be dissolved in the hydrocarbon of the Janus droplet. It will stay at the hydrocarbon and the water interface. And here she added Colloids or E. coli into the water phase of the droplets. And the Colloid is a mannose binding lactate, which can bind to up to 4 mannose and cause agglutination. Also, the E. coli is a species of bacteria that have the colloid secreted on the surface and can bind with mannose as well. So with the addition of E. coli into the continuous phase, we could observe the formation of agglutinations. And Qifan designed a very smart way to measure the formation of agglutination. And she put a layer of droplets into the petri dish and put the petri dish above a QR code. So she just used the smartphone to scan the QR code. You could see that without the addition of E. coli, the solution is transmissive, so the smartphone could easily scan the QR code. However, with the formation of agglutination, the solution become kind of cloudy or opaque, so it's hard to scan the QR code anymore. And another method of detecting bacteria is the light curve, and it was designed by Lucas. And Lucas made a bronic acid surfactant, which could stay at the interface of the hydrocarbon and the continuous phase. And you know that boric acid will have reversible binding with carbohydrate or the N-glycan on the anti-salmonella antibody. After the formation of the complex, the morphology of the liquid colloids are changed. And then he added the heat-killed salmonella into the continuous phase because there will be a competitive binding between the heat-killed salmonella with carbohydrate or the anti-salmonella antibody. So the morphology will change back to the beginning again. And the change of the morphology will result in the change of the angular distribution of the droplets fluorescent emission. So by measuring the changes of the emission intensity, Lucas was able to measure the concentration or the detection, the existence of salmonella. And after we know some applications, we want to know a little bit, maybe a little bit about the analyte we're going to detect today. It is Listeria Monocytogenes. Listeria Monocytogenes is a species of gram-positive rod-shaped bacteria. It is a foodborne pathogen, and it is responsible for listeriosis, which is a potentially lethal illness for pregnant women or the people with imparted immune system. So our research goal will try to design an inexpensive, fast, and sensitive sensor for the sensing of listeria. So as we mentioned, starting from the Janus droplet, how could we achieve the detection of the listeria? And here is a strategy. First of all, I want to describe a little bit about the chemistry. Here is a reaction. We call it TCO, tetrazine click reaction. It is inverse the Mendel-Adler cycloaddition reaction between the Trans-Cyclooctene and the tetrazine. This click reaction is very fast in speed, and also it requires no catalyst, and it can happen in any kind of buffer we're using in the biological system. So it is very frequently used in the bioconjugation. And after that, we design a polymer we call it Poly-TCO. It is a block copolymer with a hydrophobic polystyrene building block and also hydrophilic acrylic acid block. And here we also have a block of the TCO molecule, which is available for the click reaction with the tetrazine. And we put this new molecule, the polymer surfactant molecule, into the hydrocarbon of the droplets. And in this project, we were using diisobenzene as the hydrocarbon phase and HFE 7500 as the fluorocarbon solvent. We mix those two solvents at a 1-to-1 ratio, and also we adjust the overall structure to be Janus with the addition of zonal and the twin 20, the two surfactant at a 1-to-1 ratio. Here we could see the optical image of the formation of Janus droplets with the incorporation of Poly-TCO in the hydrocarbon phase. After we made those Janus droplets, we want to do the bioconjugation of the Listeria antibody on the surface of our droplets. And first of all, we try to connect a tetrazine molecule to the Listeria antibody. It is very straightforward because we let the tetrazine and HS ester to react with the free amines on the Listeria antibody and just form the amide bond. And after we get the tetrazine Listeria antibody, we put the antibody into the continuous phase of our droplet solution, and there will be a TCO tetrazine click reaction happen and lead to the formation of a new complex with the Listeria antibody to be conjugated on the surface of our droplets. We try to visualize the bioconjugation of Listeria antibody by adding protein A fuzzy into our system, because Listeria antibody is a type of IgG antibody. And the IgG antibody has very strong binding with protein A fizzy. So if there is Listeria antibody on the surface of the droplets, we should be able to observe the fluorescence when we add the protein A fizzy into the system. And as shown by the confocal image, we could observe very strong green fluorescence, indicating the successfully bioconjugation of the Listeria antibody to our droplets. And after we confirm the binding of Listeria antibody, we wanted to do the agglutination assay. At the beginning, we added heat-killed Listeria monocytogenes into our system. And since the one heat-killed Listeria monocytogenes can bind to more than one antibody, so it should be able to lead to the formation of agglutination. And as shown by the optical images here, the upper panel is after we added 10 to the 7th CFU per mil of Listeria antibody, heat-killed Listeria into the solution, we could observe the formation of massive amount of agglutinations. And we could see at different magnifications, it's very clear that the Janus droplets are tilted and form the clusters. We keep decrease the concentration of the heat-killed Listeria to be added into our system. And we find that when we add 100 CFU per mil of heat-killed Listeria into the solution, we could still observe the formation of some agglutinations, indicating that our system actually is very sensitive, that we could detect the heat-killed Listeria at a concentration or at or above 100 CFU per mil. Those are just some qualitative images, and we want to get the quantification of agglutination assay. So we just use the image analysis to do the quantification. So the image processing code transforms the optical micrographs into grayscale images and then measures the average droplet diameters. To locate the agglutination sites, the program distinguishes the darker areas, as shown in the picture, where multiple droplets are tilted off their natural axis. And using the average droplet diameter and the area of the darker region, it then calculates the percentage of agglutination. Using this information, we could create a calibration curve that relates the percentage of agglutination with the increase of the number of heat-killed Listeria to be added in the system. Although we have this quantification method, we still want to create a more robust quantification method that we could produce a new fluorescent signal. Here is how we did that. We introduced 2 dyes into our Janus droplet system. We call it 2-dye system. One is FPBI dye, which is a fluorocarbon soluble emissive pyridine dye. And the other one is sub-PC. Sub-PC dye is a blocker dye, and it is only soluble in the hydrocarbon phase. And this picture shows how those 2 dyes are incorporated into our system. As we mentioned before, the polymer Poly-TCO is dissolved in the hydrocarbon phase, and we also dissolve the sub-PC dye in the hydrocarbon phase, and the emissive fluorescent dye FPBI into the fluorocarbon phase. And because of the fluorocarbon has a higher density, and due to the gravity, the fluorocarbon will stay at the bottom and the hydrocarbon will stay on the top. As shown by the optical image of the 2 dyes dissolved in their own phases, we could see that the sub-PC dye only dissolves in hydrocarbon phase and the FPBI dye only dissolves in the fluorocarbon phase. And we also showed the fluorescent spectra and the UV spectra of those 2 dyes. We could see that when excited by wavelengths at 361 nanometer, the fluorescent dye FPBI will have a maximum emission at around 580 nanometer. And from the UV-vis spectra of sub-PC dye, we could see that sub-PC dye is actually a very good blocker dye. It could absorb both the excitation light at 361 nanometer. Also, it could absorb the emission light from FPBI at around 580 nanometer. And I'm going to talk about the detection mechanism very soon. As we mentioned before, we were able to get agglutination when we add heat-killed Listeria into our Janus droplet conjugated with Listeria antibody. So we want to test if it still works for the droplets incorporating those two dyes. And we did the same experiment with the addition of heat-killed Listeria. As shown by the optical images, there is clearly a lot of agglutination formed when we added the heat-killed Listeria. Then we moved to the fluorescent spectra sensing scheme. We put a layer of droplets in the Petri dish, and we also placed a bifurcated fiber right above the Petri dish. So the the excitation light and the detector are both on the top of the dish. And as mentioned before, because the density difference, so the fluorocarbon will stay at the bottom and the hydrocarbon containing the blocker dye will stay on the top. When the excitation light want to get to the fluorocarbon layer, reach the fluorescent dye, it has to pass through the blocker dye layer first. And because the blocker dye has very good ability of absorbing the wavelengths at 361 nanometer. So most of the excitation light actually will be blocked by the blocker dye, and only a tiny bit of the excitation light will get to the bottom layer and try to excite the fluorescent dye. And in this case, the fluorescent dye will emit emission at around 580 nanometer, and because the detector is on the top, so the emission want to be detected, it has to travel back to the top, and so the emission will have to pass through the blocker dye layer again. And as we mentioned before, the blocker dye also have very good property of absorbing the wavelengths at around 580 nanometers. So it will just try to absorb most of the emissions from the emissive dye. And in this case, the detection on the top will hard to get the fluorescent signals from the fluorescent dye. However, with the addition of the Listeria, there will be the formation of agglutination. And because of the formation of agglutination, a lot of the droplets are tilted. And in this case, we could see that the fluorocarbon dyes are exposed to both of the excitation light and the detector. With the formation of higher amount of agglutination, there will be more fluorocarbon phase exposed to the detector and excitation wavelengths. And we using this scheme, we did measurement of the fluorescent spectra. And as shown in this picture, we could see that those when we add different concentrations of the heat-killed Listeria into the system, and we could observe the maximum fluorescent intensity at around 580 nanometer, and with the increase of the concentration of heat-killed Listeria to be added in the system, we could observe a higher fluorescent intensity. And on the right is the correlation curve of the concentration of heat-killed Listeria and the relative fluorescent intensity at 580 nanometer. And we could see a general increasing trend, which is inconsistent with our optical images, also with the common sense, because there will be more agglutination formed with more Listeria added. And using this scheme, we could detect the existence of Listeria at or above the concentration of 100 CFU per ml, which is a very, very low detection of limit. And as we mentioned before, we were using heat-killed Listeria. And because we want to test the real world sample, so we tried to add live Listeria into our system to see if it still works for the, if we could still get agglutination with live Listeria. So after we add live Listeria at different concentrations into our system, as expected, we were able to observe the formation of agglutinations, and with a higher concentration of live Listeria added to the system, we were able to get more, the larger number of agglutinations formed. And similarly, we did the fluorescent spectral measurement, and we found that the correlation of the concentration of live Listeria with the relative fluorescent intensity at 580 nanometer is also get a similar trend that with a higher concentration of live Listeria added, there will be a higher fluorescent intensity at 580 nanometer. And also we could get a detection of limit at 100 CFU per mil. So all of the experiments we did previously, we just put the detector and the excitation wavelength on the top of the Petri dish. So the light have to travel through the solution to reach the bottom layer and to reach the droplet layer. And for some real world sample, there might be some scattering impurities in the solution. So we were thinking it will be better if we could detect the fluorescent signals from the bottom of the Petri dish, so that we don't have to, the light doesn't have to travel through the solution. That's why we designed the inverted two-dye system. In this system, we use the same Janus Droplets, and we incorporated commercialized the fluorescent dye, which is Lumogen Orange 240. We put that in the hydrocarbon phase. And we also made and designed a new dye we call F sub PC. It is a fluorocarbon dissolvable sub PC blocker dye. It will be able to block excitation light and also the emission of the Lumogen orange at around 535 nanometer. In this case, we put the excitation light and the detector on the bottom of the Petri dish. So the blocker dye will just block the excitation light as well as the emission from the Lumogen orange. And so without the addition of Listeria, there will be very low signal to be detected. And similar as the two-dye system, when there is formation of agglutination, we should be able to have more hydrocarbon containing the fluorescent dyes exposed to the sensors. So it will get an increased signal. And here is the spectra, the fluorescent spectra we mentioned. After we excite the system at 400 nanometer, and we could see that with the addition of different concentrations of live Listeria in the system, we could observe a maximum fluorescent intensity at around 535 nanometer. And with the increase of the concentration of live Listeria, there will be an increase of the relative fluorescent intensity at the maximum emission at 535 nanometer. And similarly, we get a limit of detection at 100 CFU per mil, which is consistent with the two-dye system. After we talk about the lab work, so much of the work that we're using the lab equipment, I want to talk a little about the smartphone stuff, because sometimes we want to apply our technique for some if you can have a homemade device to get the bacteria to be detected, it will be very good. So we were thinking if we could make a very simple setup, and if this setup will be able to figure out the formation of agglutination or not. So we bought this very cheap 20x microscope and put that onto our smartphone. And we use this new smartphone microscope setup to take pictures of the non-agglutinated or agglutinated droplets. Here are the results. You could see from this picture, upper panel, we contains the picture, upper panels are the pictures with higher magnification, and bottom panels are the image with lower magnification. But we could clearly tell the difference with our naked eyes about the droplets without the addition of Listeria or with the addition of Listeria. You could see that there are some formation of the brighter bluish clusters, and when there are formation of agglutination. Also for the lower magnification, you could tell the difference. So we are able to apply our technique using our very frequently used smartphone. And you don't have to only rely on the lab equipment, which are pretty expensive for the daily use. And in summary, I'm going to, a quick summary. And in this talk, I just described how we were using the Janus droplets as a biosensor for the sensing of Listeria in the daily life. And by incorporating the two dyes, a pair of emissive and the blocker dye, we were able to use the fluorescent spectra to quantify the level of Listeria in the system. And with that, first of all, I want to thank my PI, Professor Tim Swager, for his support in my project, also for the very helpful advice and the discussions. And I also want to thank Brian and Emily for the daily help. And I want to thank my co-workers, Suzhou, Zach, and Kosuke for the contribution in our project. And I want to thank the entire Swager group. Thank you all for attention. I'm happy to take the questions.
Okay, thank you, Jie, for that talk. It was great, and also for any of you that want to ask questions, just raise your hand and I'll call on you. And there's the first rule of questions is there's no such thing as a dumb question. All questions are good, and usually there are a number of other people who had the same question when you ask it. So the floor is open for questions. Vladimir.
Yeah, it was a great talk, and I very much appreciate it. I'm wondering, what is the state of the art? By how many orders of magnitude or factors of 2, or are you approaching it or exceeding it when it comes to this kind of detection?
Excuse me, what do you mean
so,
by?
The detection of Listeria, call it as a substance we might want to be able to detect. Others are trying to probably do the same and develop their own techniques.
Yeah.
So how does your technique compare to the state of the art of detecting Listeria?
Oh, actually, other people also did the, as you mentioned, yeah, they were doing the Listeria detection. And so far, we could achieve the 100 CFU per mil of the limit of detection. And when we keep increasing the incubation time, we could get the lowest, in our technique, we could get the lowest detection of limit at 20 CFU per mil, which is already, so far, I can see some literature, they have like 100 CFU per mil or like 10 or 20, but I think we're good. We are the one of the having a very good sensitivity of the Listeria detection.
So is it reasonable to consider this technique to be commercialized? Or what would be the challenges to commercializing, maybe is another way of putting the question.
Yeah, I think it is this project should be very good for being commercialized. I think the most I think one of the challenge will be how we could get the setup in the very small device and get it to be used in the, as I mentioned, at home. You don't have to come to lab. And so far, I think our technique is we could use, as I mentioned, use a smartphone technique to take a picture of the thing. And I guess maybe one of the problem will be the long-term stability of the droplets, because our droplet could be stable already for several months or even for years. But if you want to keep the thing for like 20 years, it might be the problem. So yeah, we are now still doing some other works, like trying to polymerize the droplets to be particles. So I think that will help to increase it.
Yes, I think Gia is being very careful about what she says, but there is a startup company, Vladimir, called Zybus Systems on this, and then also in terms of, it's all about food and beverage testing. But Gia has actually created some preliminary results on inflammation monitoring that could be done at home that she didn't talk about today, but it actually, those preliminary results really key. And we now have a new grant coming in collaboration with Bevan Inglewood and bioengineering that we hope to basically create technology that can be used to monitor immunotherapy and help physicians basically optimize treatment of cancer patients by being able to monitor inflammation responses that they get through that. So there's some big things brewing on the side. We think this technology or different variants of it that are more stabilized, and Gia actually does have another version of this that is more stable that she's not telling you about right today, but it's in the works, and it works.
Well, Gia, that simply means we'll have to invite you again to join us for another Nano Explorations in a year from now.
Okay, so Charisse gave me some instructions, which I haven't followed very well, but the one thing she did want me to do this was all recorded, but also so you can watch it over and over again if you want. But on December 22nd, we have another lecture in Nano Explorations coming up by Abhishna Kumar, and stay tuned for that.
Thank you all.
Okay,
Thank
bye-bye.
you.
Bye-bye.
Bye.